I should have coffee before I said the record button. So in question 25b, so you have a kind of a scary looking question, right? So from here, right, the goal of this question is to show that we can take derivatives or antiderivatives rather iteratively. So sometimes we don't want to keep going through these trig processes, right? So we can kind of find a nice easy formula that we can use, and in tangent we have that case. So we just showed a moment ago that we could take the antiderivative tangent. If you were trying to take, say, the antiderivative of tangent squared of x, well, you can use a trig identity to say that this is the antiderivative of secant squared of x minus 1 dx. And you could then think of this as the antiderivative of secant squared minus the antiderivative of 1. Both of those have some dx's with them. So the antiderivative of secant squared, that comes from tangent. So that would just be the tangent of x, and then minus x plus c. Right, so we can also take the antiderivative of tangent squared, right? So we tangent squared, we got some antiderivatives there. But when we start getting the tangent to the third, fourth, fifth, right, we can run to a little bit of a problem. So let's look at tangent of something raised to the nth power. All right, so n is going to be greater than or equal to 2 because we just shown that we could take an antiderivative tangent to the first power to the second. So the idea here is we want to pull out a tangent squared. Right, so we want to take this tangent of n minus 2, a tangent of n, and write it as the tangent squared of x. If I pulled out 2 copies of the tangent, I'm left with n minus 2 of x dx. So once we get it to this step, well, we can say tangent squared of x is just secant squared of x minus 1. And then tangent of n minus 2 is just tangent of n minus 2. And if we look at what we have now, right, we can make a nice, healthy u substitution, right? So I could distribute this to both terms. So this is going to be the antiderivative of tangent of n minus 2 x times secant, that's the times, secant squared of x minus tangent of n minus 2 x dx. That's dx here as well. I'm going to just give that integral to both because I can do that. So this might not look like it's that much healthier. I don't know, healthier is not the right word. This might not look like it's that much better. But over here in this kind of left integrand, notice that if we say, let's let u equal just the tangent of x, then du is secant squared of x right there hanging out. So we could take this integral and write it as u to the n minus 2 du. If we take this antiderivative, well, it's simply u to the n minus 2 plus 1, so the n minus 1, all over n minus 1 plus a constant, aka the tangent of n minus 1 x over n minus 1 plus a. So we have that as our antiderivative. And so we can say now that we have the tangent of n of x is currently equal to the tangent of n minus 1 of x over n minus 1 plus a constant. But I'm going to throw this constant in. I'm going to put a constant plus all of that garbage. Plus, well, we still have another antiderivative we haven't taken, right? This tangent of n minus 2. So we have minus the antiderivative of tangent of n minus 2 x dx. Now, one of 3 things is going to happen, right? So either, number 1, the n minus 2 is equal to 1. In this case, we're done because we know how to take the antiderivative tangent. We would just take the antiderivative tangent. We would get to negative natural log of cosine and be done. 2, we could say n minus 2 could equal 2, right? So if this were 2, then we can also take the antiderivative of tangent squared. It would be tangent of x minus x plus a constant. So in that case, we'd be done. Or, bad news, n minus 2 is still greater than 2. So in this situation, if it is greater than 2, we just would repeat the process again, right? So we would just say, okay, I would pretend that I had this integral. I would focus on this integral here. I would pull out a tangent squared of x times tangent of n minus 4 x dx. And we'd play the same game, right? We'd say, all right, so tangent squared is secant squared of x minus 1 times this tangent of n minus 4 x dx. We would do the same distributing thing. We'd end up with negative tangent of n minus 4x secant squared of x minus this antiderivative. They're both going to be minus. That's actually going to be a plus. Plus tangent of n minus 4 x dx. So we would make the same type of u substitution here. I'll leave it to you to show that that's going to be tangent of n minus 3 of x over n minus 3 plus a constant, which is going to get sucked up into whatever constants we have, plus now this antiderivative right here. So we can repeat this process again, right? N minus 4 is 1, we're done. N minus 4 is 2, we're done. N minus 4 is greater than 2. Well, we just keep repeating the process over and over and over and over and over and over and over again, right? So we've shown so far that this integral here is equal to some constant plus this, plus this, plus this, and this will go on and on and on and on and on and on and on until you're done. Until you reach like the end, that is either a 1 or a 2, that is by done.